just they're not, you write your matrix A, I, J. They're not just like that. They have very special structure. You should know your matrix, and generally, it's not something that you should just send off to a matrix. A one-dimensional matrix, yes, but not when you're in 2 or 3D. Let me give a method for solving, say, the Poisson equation in 2D. Here's the, or either the Poisson equation or, am I taking the Poisson equation or am I, no, actually here I'm just taking the second derivative. I'm taking the second derivative. I think I'm not, no, either way, either multiplying or solving, it's going to be the same. Okay, so this idea that your diagonal in the other directions goes as follows. You have your second derivative in x, second derivative in y. You can decompose, this is an nx by nx matrix. This is an ny by ny matrix. You can diagonalize it. That means you're writing the operator in terms of a matrix of vectors. The ex is the eigenvectors. This lambda x squared is the eigenvalues of the second x derivative. It's a diagonal matrix. And this is the matrix that brings you, that has the inverse, that's the inverse of the eigenvector matrix. And this is a point that we brought up before, a couple of classes before. Look what I've done. I have moved my EX and my EYs over here, my EX and my EYs over there. What allowed me to do this is commutation. X operators and Y operators commute. I didn't really write this as well as I should because these matrices, you can't, they're full of zeros and I should have used direct products and things like that. You see what I mean? This is not the same size as this. I can't really multiply. But what I mean to say here is what I was saying here. I'm doing an X operation, and I'm doing it for every Y. I'm doing a Y operation, and I'm doing it for every X. Okay, so I should have a more complicated notation here. But what I mean to say is, we take this P. I mean, this thing here is a full matrix. But it's not just any full matrix. We take this Pxy, we take it to eigenvector space in Y. That's an operation like the one that I mentioned there. That takes a time, and y squared, but it is linear in X. We take it to eigenvector space in X. That takes a time like this. Once we're in the eigenvalue space of both of them, the Laplacian is diagonal. So that's an operation. All you have to do is divide by nx, and there's one eigenvalue for every x and y. And then we come back from eigenvector space in x. We come back from eigenvector space in y. And our total operation count is like this. So something like what I was doing there. Despite the fact that it's formally a matrix multiply of a matrix that's nx and y by nx and y, and hence should have taken a time that's nx ny times nx times ny. It takes much less time than that. And keeping in mind nx is something like 100, that's a savings of 100. So this is one way of taking matrix multiplies or solving. It doesn't matter which you're doing because you can easily invert a diagonal matrix. A diagonal matrix, the inverse of a diagonal matrix is, of course, the matrix consisting of the inverses of everything along the diagonal. And this is a possible way even to integrate in time. It's not widely used, and I don't think it could be. I once did. I don't really have much more to say about it, but formally we can do the same thing. That is to say, if we want to multiply by the exponential, well, how do we take the exponential of a matrix? We talked about that in the very first class. Well, all we need to know how to do is take the exponential of the diagonal matrix consisting of the eigenvalues. We go to the eigenvalue space, the eigenvector space, by multiplying by these matrices one after the other, and that takes a time nx and y squared plus nx and y squared plus nx squared and y. Once we are in eigenvalue space here, we can just multiply through by the exponential of the eigenvalues. It takes a time like this, and then we come back. So these operations are quite feasible because of the commutation between x and y.
I think in the Poisson equation, in the last, equality, no, above, no. Yeah, in the Poisson equation.
Yes.
Yeah, I think in the bracket, I think the plus should be some common.
So this should be somewhat?
Common. Because in between it's
No. I mean,
it's not a plus.
you're right. I'm sorry. You're right. This is what I said. This notation is all bad. I shouldn't have written it this way.
Okay.
This should not.
I understand it.
No. You are right, but let me clarify this for everybody.
Yeah.
That's right. As I said, all these matrices are of different sizes. There's no reason why you can't really add them together. I shouldn't be writing that. I don't know how I came to write that. I shouldn't have been writing it that way. I should have written, when I wrote that, okay, let's say we have less x values than y values. Then we have a little, here's an nx by nx, and I have lambda x1, lambda x2, lambda x3, and so on. And then I have a matrix that, like this, lambda y1, lambda y2, lambda y3. I can't add together those matrices, and I can't multiply together these matrices. This is an nx by nx matrix, this is ny by ny matrix. This is bad notation. I should not have used this notation. What I should have done, let's just go to this one. Okay, what I should have done is made a matrix that was like the one I was just describing before, where I have here, I've listed all my, this is nx, and then I have another nx. This is iy equal 1, iy equal 2. This is a matrix this is of size nx and y by nx and y. And I have here all the I have lambda 1 x squared plus lambda 1 y squared. And then here I have lambda 2 x squared plus lambda 1 y squared. And I have a diagonal matrix. And what I really should have written, and I'm not ready to do it right now, is something along the lines of something like that. I'm sorry, maybe I'll be able to clarify that during the break. I'm sorry. I think everybody gets the words for it. We have decomposed pxy into modes in x, the eigenmode vectors in x and eigenvectors in y, and for each eigenvector in x and y, we operate with this, and then we go back, but I haven't used the right mathematical notation. It's bad enough. There's no pluses there, no times. They all have the wrong dimension. Okay, I'm sorry about that. Okay, so in fact, I guess we should say the matrix that I'm calling that is not an nx by nx, but it is, say, something that is nx by nx times a delta function in y. Something like that. This is a maybe this is, okay, so I would have this eigenvalue matrix would be something, would be a function of ix, iy, jx, jy, and it would be equal to, it would be diagonal in x and diagonal in y, and then I would have something like this. Does that look better? Something along those lines? okay, so it's, that's, everybody understand what I'm, all these delta functions mean that this thing is very, very diagonal, with a lot of zeros. Okay, and that's really what I should have written. Okay, we could say that what I mean by this is this. No, is this. And then what I mean by the other one is this. But you're not going to store it as these full matrices. And the same thing with the EX and EY. This thing, if I'm really going to multiply that, there's delta functions in Y to make it of the full size. But yeah, this is really very illegal notation. So what we've shown is that acting with the Laplacian or the inverse Laplacian or the exponential is inexpensive in a tensor product grid. Tensor product grid meaning this very thing that we were saying here. It's a sum of these operators in different directions. That would also be the case more or less in cylindrical spherical geometry. It's more complicated, especially in cylindrical, because the R's get mixed in, but it still can be done. And that's, so it's inexpensive in a tensor product grid for spectral methods or finite difference methods. In finite difference methods, you have lines like this, you know, and again, in same thing in curvilinear coordinates. In spectral methods, you have functions of x times functions of y times functions of z. So that's the main thing I know about. More flexible geometries require something other than a single grid or a single basis, and you have finite elements or spectral elements or finite volumes, and those are the kind of methods that you use when you want to design an engine or something. And so they have, that you can't do things quite so simply, but they all have tricks of their own, which I don't know, that allow you to invert or diagonalize matrices, especially invert or multiply matrices by vectors in a way that's much faster than mere send the matrix off to a matrix vector product. Okay, so let's talk a little bit about spatial discretization. The two things I know about are not things that engineers use. Perhaps engineers use them some, but most of the engineers are using finite element or finite volume. But anyway, many of the ICKs are the same. Finite differences, you represent your function at grid point values, and you take combination of those grid point values to get derivatives. Spectral, you represent your functions as coefficients of basis functions, and when you want to differentiate, well, you can do that exactly in that you know the derivative of the basis functions, and so you can represent your function by you can do your derivatives exactly. And the spectral is especially convenient for periodic boundary conditions where derivatives are diagonal operations, where you can use Fourier series, or in spheres where you can use spherical harmonics. For a spectral method, as I said, you can do these derivatives exactly. Of course, the method isn't exact because you have truncation. Obviously, you cannot represent any function as a superposition of a finite set of basis functions. You know, you're truncating your Fourier series, but your derivatives, these are derivatives that are only exact for, say, okay, this will be exact, I think, for a quadratic function. Am I right? Is it? I think it's exact for a quadratic function. Or, yeah? Okay, but not for a cubic function. These are exact, these do not have that kind of error. Their error decreases faster than 1 over the number of grid points to any power. That's why one says sometimes it has exponential accuracy. Formulas like this is second order accurate. It matches the Taylor series. For the error is in delta x squared. Am I right? Or delta x cubed? You seem to know about it. Nodding back. So these are second order accurate formulas. You can make more higher order accurate formulas, but these are higher than any power. The error doesn't go like delta x squared or cubed or fourth. It goes faster than that for any power, and it's called exponential.
Excuse me?
Yes?
I didn't understand, like in the spectral one, UXX, sigma, UM, pi, double prime.
You don't like this because you can't differentiate this? Is that, no, I'm sorry, go ahead.
I mean, how these two are equal? Like,
No, this, again, my notation seems to be really poor. This is, yeah, sorry. I should have called this some other letter. This is, no, yeah, very poor notation, really, really bad. I don't know how I could have used such poor notation, and me in math, what a scandal. What I mean is that I should have written phi mm prime is equal to some sum, say, of d m j phi j. Right, you agree with this? Right. And so then I should write um phi m double prime somewhere is equal to j d m j phi j, right? And then I should write this, I'm going to change the letters. I'm going to call this, I'm going to switch the letters. Okay, you're going to let me do that? J, U, J, M, D, J, M, phi, M. Right, that's okay. And then I'm going to write the whole thing as M, J, U, J, D, J, M, phi, M. So this is the thing that I am calling UM double prime. Right, that's really what I should have written. Okay, please excuse the bad notation. It's a very, not worthy of a somewhat mathematical training. Shoot. But this is okay? Yeah, okay. Thank you. Oh, to think that these things are preserved for posterity. Okay, thank you for being alert and catching these things and not letting me go off into bad notation land. I'm very glad that you're there and asking these things. Any other questions or comments, corrections? Yeah? It's okay? Okay, so the spectral methods were thought of for a long time until the 1970s, but it was considered too difficult because what you had to do multiplications in Navier-Stokes, and to multiply two functions which you have in physical space. If you have, supposing you want to know f g at xj, well, that's easy. That's f of xj times g of xj. Right? That's an operation that takes the number of grid points, period. Whereas if you have f as a sum, f m phi m, and g as a sum, g j phi j, to take that sum, to do the product, you're going to have to do these kind of manipulations, and it will take a time n squared to do that. Okay, so it's thought to be true. But then Orszag had the idea that what you should do is do the multiplications. You should have both representations. You should have a representation as grid points and also as basis vectors, and you could go from one to the other by Fourier transforms. And as we just discussed, Fourier transforms are very cheap. And it's not just okay, and when I say Fourier transforms, I don't just mean Fourier transforms. It's the same if you went to any basis vector. If you're a tensor product basis, those operations are diagonal. They decouple because operations in x and operations in y commute, and so that they don't cost a full nx times ny squared. So you can do a transformation between the grid points. If you have a representation in 2D with grid points, you do not have to go to the space of the basis functions. Will take a time like everything that we were discussing here. Will take a time like this times nx plus ny, because going to the basis in x is going to take a time nx squared, but only ny of them. And going to the basis set in y will take a time ny squared times nx. So it's cheap to go to the basis. You can go to your basis, do your derivatives, then come back from the basis and do your multiplications. You can do each step, each operation in the step in which it is cheap. And So this combines speed with the high accuracy. And the operation, you can do this in your pictures of various tensor product domains, a Cartesian, a cylindrical, and a spherical. Okay, so that I believe that this is the fastest way to do numerical methods for those domains. I'm not saying anything for tubes and engines and helicopter blades, which have more geometric complexity. But if your domain is like this, I think pseudospectral is superior in all ways. High accuracy and the same price as finite difference. So here are the pictures in which you cannot have a tensor product basis. You fill this you probably know better than me, you fill your complicated domain with rectilinear elements, and then you fill each element with a grid or with basis functions. Okay, again, something I know little or nothing about. Parallel computing, one of the main ways that it's done is to decompose your domain, your big domain, into smaller domains, and each one is associated with a processor. Or you can associate a set of Fourier modes with each processor. Both are done. Okay, and what's usually done in Navier-Stokes is a mixed implicit-explicit method where you use an implicit method for the viscous terms for the reasons that we talked about, and an explicit method for the nonlinear terms. And why would you do that? Well, this is kind of like multiplying by nu k squared, and this is kind of like multiplying by uk. No, I'm sorry. Why would you do that? First, I can say, why would you do that? Well, because recall that implicit methods require you to solve an equation, and I was emphasizing how difficult it is to solve even linear equations. But when you talk about nonlinear equations, well, that's a whole other ballpark that's harder. Linear equations you always can. It might be costly, but in general, there are tricks that make it not costly. But even otherwise, even if it were costly, it's always possible, well defined. Solving a nonlinear equation is may not even be possible. We do it numerically, Newton's method, this and that, but it's not a procedure. Hence, there's a good reason why you would be implicit in the viscous terms and explicit in the advective terms, because it's possible to solve a linear equation and not necessarily possible to solve a nonlinear equation. Okay, that's one. However, by good luck, it turns out that the big constraint is from the linear terms. It could be, why should you do it? If your constraint in time is going to come from the nonlinear terms, then what's the point of doing this one implicitly, being able to take the large time steps? But no, you can't take the large time steps because of this. Because it turns out that this is more of a constraint, and let us figure out why. Or for the Reynolds numbers that I deal with, it's more. It could be that at high Reynolds numbers, that's not the case. I haven't looked at this very much, but in the Reynolds numbers I deal with, it's definitely the case. So this is kind of like multiplying by nu k squared. So the worst it can be is the highest k, which is the smallest delta x. This is kind of like multiplying by by the maximum u times the maximum k here, kind of like. And if you can make a kind of pseudo Reynolds number, what's called a grid Reynolds number, by combining these this way. That is the ratio between these two. If you take u max, k max over nu k squared max, you get this grid Reynolds number. And in fact, what you're supposed to do is keep that less than 1. That's a kind of guideline for your for resolution. So even though you might be increasing your Reynolds number, meaning decreasing your nu, yes, that's true, but as you do that, you are also increasing your k, decreasing your delta x, because you get smaller and smaller spatial scales as you go up in Reynolds number. And so those two effects counteract each other. You have smaller nu, yes, but you have bigger k. Okay. I'm not absolutely sure about this. This is something these are conclusions I've come to myself, and they make sense, but I am not absolutely sure of this. There may be something I'm overlooking, and I encourage, if you find something that contradicts that, please write to me, tell me about it, and it could be that I'm wrong in this analysis. However, there remains the possibility that people are they do use implicit for viscous, and they do use explicit for advective. And so if I am wrong, then they are wasting a lot of time doing their implicit viscous. They should be also doing that one explicitly. If this is the limiting step, then they're wasting time. Okay, so now let's get, yes.
I'm just curious, like, I mean, when if you were to code this up, you will have to time match your solution on your right hand side. But then if you are using two different type of temporal scheme, one is implicit and one
Yes,
is
yes.
explicit, with two different delta t's,
Yeah, no, you don't use two different delta
you
t's.
use same delta
Same
t.
delta t.
And what is the advantage actually
What is the advantage of what?
of using such a? It's just for the stability reason.
Oh, just for the stability. Yes, for the stability, that's right. Yes, that's right, it's for the stability, yes. I mean, this is the problem in time integration, is stability.
So are you saying that basically if you use the implicit term for the
Viscous terms.
for the viscous term, what does that tells you about your delta t? How much
Your
more
delta
bigger
t is, okay, of course your delta t is limited in any case by accuracy. I mean, it's nice that your solution doesn't blow up, but it could still be the wrong solution. You know, if delta t is very large, okay, you're not infinite, but you're wrong because all this is based on Taylor series and it stops being true. If you take a scheme that's very stable and if you take delta t of 100, then you know, your solution won't be right. So certainly, you can't being stable isn't the only thing.
Yeah, you still have to ensure
Okay,
that
but you still have interactions, so you do have to take delta t kind of small. You also have another thing governing your delta t is that you need to take it small enough that your nonlinear term, the one that's being done explicitly, is stable. The guideline that I was taught to use, again, I'm ready to believe that people who have really studied this is wrong, is that those two are very similar. That is to say, you can judge your accuracy about, you're becoming inaccurate when your nonlinear term, when you blow up because of your explicit one. Generally, the people that I know choose their delta t such that their overall scheme is stable, meaning that they have not violated the stability criterion for the nonlinear integration of the explicit integration of nonlinear terms. But it didn't have to be that way. It could be, I mean, and you should also always test for accuracy also by, you know, if you have an important result, you better check that it's true when you take delta t to be half of what it was before, and make sure you get the same thing before you publish something that is going to make you look embarrassed if it's not true. Have I answered your question? But what you don't want is to be constrained by the, okay, what are these things? For very high k, these are little tiny, they're things like this. They're supposed to decay. The higher the wave number, the faster the decay. They should be squashed. But if you use an explicit method for this, this grows instead of being squashed, and that's what you don't want to do. It's kind of like a parasite. Okay, so maybe it's a good time to take a break. We take a 10-minute break or so. Okay, I'll try to really make it 10 minutes. I know the breaks have been kind of becoming 20 minutes.
So
but
like comparatively speaking,
yes.
if you were to solve this equation based on a full explicit scheme, when you solve it in this manner, basically because you use the implicit for the viscous term, you can have a
Explicit, you mean, no?
no, for the viscous term.
I know, but right now you said a full explicit
Yeah,
method.
compared to the full explicit.
Full
scheme.
explicit,
So,
yes.
Relatively speaking, solving it in this way will just give you you can use a slightly larger delta t.
Not slightly.
How
Much,
much,
or maybe 100 or something. It depends on what your spatial resolution is. But much, much larger.